Hello, everyone. Thank you for joining me today. I'm Zakaria Khloufi. I work for TenneT as market analysis. Today, I'll walk you through how we use PLEXOS to model our national adequacy study. It's called Monitoring Levering Zekerheid, so I will call it just MLZ from now on, then it keeps it more short. I chose for a title today from scenario to adequacy decisions because people who work really with such studies, they know that the most issue, like the challenge that we have is not only how to model in PLEXOS or how to run simulations, but also how to translate our scenarios into adequacy indicators. I will be focusing on three main things: how to assess resource adequacy, the modeling choices for this study itself, and the lesson learned after running this study for at least 3 or 4 years now using PLEXOS. Before going into the study itself, I would like to show you TenneT PLEXOS study landscape. So within PLEXOS, within TenneT, we use PLEXOS to answer different questions, starting from operational studies like the backtesting, where we try to validate our data against historical data, to the new European study flexibility need assessments, where we are trying to quantify the ramping need, risk curtailment needs, and the short-term needs, to strategic planning, where we try to look at grid investment, like in investment plan, or capacity expansion, like the energy system optimization study, to resource adequacy study, of course. The main study the adequacy study, we already have the European one, if you are already aware of, is European resource adequacy, where we really look at the resource adequacy indicators for whole Europe. Both studies, MLZ and ERA, are really similar in the way that they are being modeled. The only difference is that in MLZ, we use our own Dutch assumptions and our own sensitivities. In European data, we look at all Europe based on the trend scenarios. Why I chose the MLZ study itself? I would say because currently MLZ is the most complete PLEXOS use case at TenneT. So it's a combination of scenario design, European simulations, Monte Carlo simulations, scarcity analysis, and economical viability analysis. I will go through all of this later on. Let's go now a little bit into what is the MLZ study. So with the MLZ, we are trying to answer the adequacy questions. Can available resource meet demand under future stress scenarios? So we assess whether the demand can be met by generation, storage, demand-side response, and imports. We don't really look for grid issues like voltage, redispatch, or they are outside the scope. We do model all Europe as flow-based market coupling, but we don't look further into the grid bottlenecks. The study itself is a yearly product of the Netherlands. We look at roughly at coming 10 years ahead. So we look, for example, we model target years. We call them as a target year. We model 2030, 2033, 2035. And it's a legal mandate. It means that our findings feeds the government about some indicators, which are the LOLE and the ENS. If you are not familiar with this terminology, the LOLE is the expected hours per year in which the generation is exceeding the imports and, which demand is exceeding the available supply and imports. So in short, the LOLE is nothing than the duration of scarcity, and the ENS is the volume of scarcity. For a resource adequacy study, it's not, I would say, normal to just take an average year and you say, this is my final results. It's more important to look at a combination of weather scenarios and outage sample. That's why we call Monte Carlo simulation, because if you look at only an average year, you can overestimate or underestimate the number you have. There is a methodology behind how we select the weather scenarios and the outages. I'm not going to go through this because at least it needs an hour to explain how these are being done, but you can check how these Monte Carlo simulations are being done. Why this matters? Scarcity is rare, as I said, weather-driven and cross-border. Static capacity margins cannot really capture how often shortage happened and when it happens. That's why we perform Monte Carlo simulations. Now I will go to the MLZ workflow. I keep it really simple for now to not go into more details. But as every study, we start with the input data, where we take our Dutch assumptions and scenarios and sensitivities for the Netherlands. Because it's a European study, we model all other Europe countries from the ERA scenarios. So there is the data and the PMDB data in the ERA. It's where we take the data for other countries. Then we feed the data into our model builder. It's a converter that is being built within TenneT, where we create the XML PLEXOS file and the CSV time series. After that, we run a PLEXOS and hourly simulations, Monte Carlo simulations, as I said. So we run PLEXOS for multiple target year, for multiple weather scenarios, and we extract the outcome through PLEXOS API. We extract different properties, such as the dispatch, exchange, scarcity, and revenues. After that, we have three main branches for the study. Just to not confuse you, after we do the third run, like PLEXOS in the third point PLEXOS, when we do the simulation, we already have some values, average LOLE and unserved energy across the weather scenarios. The issue is that when you are having flow-based market coupling in the simulations, the unserved energy is allocated randomly in the system. So you cannot just take these values that you got from the third run as the final unserved energy in the system. That's why I created, actually, with Energy Exemplar a few years ago, a model in PLEXOS where we post-process all these hours where we have unserved energy, and we try to redistribute the ENS proportionally across the countries, because that's the only way that we can get the final unserved energy and LOLE correctly in the system. Otherwise, if you take just the final simulation, you will either overestimate or underestimate unserved energy in Europe. And the same methodology where we use also in ERA study. The second check is the economical viability check. So we check whether the resource remain feasible or not in the future. And the last one is the missing capacity analysis, where we quantify how much capacity the Netherlands needs to meet its LOLE target. I didn't speak about the LOLE target, but just for your understanding, all countries in Europe, or most of them, have something we call reliability standard. It means that what is allowed of LOLE hours within your country. In the Netherlands, the allowance is 4 hours, which means when we average the whole simulations across weather scenarios and sample, if the LOLE in the Netherlands is equal to 4 or above 4, then it means that we have adequacy issues. That's why we are trying in all our simulations to quantify the values of the LOLE. If it's above 4, then we are, or equal to 4, then we have an issue. And that's why we added this missing capacity analysis. We quantify how much capacity will be needed to reduce these LOLE targets to lower than 4. And at the end, we have specific dashboard that we publish the results from the MLZ study. And as I said earlier, the outcome fits into our governments regarding the outcome of the study. The design principle is something very, very important, because this study, it's really, we do it every year. As you know, every year we have new assumptions, we have new modeling choices. Traceability is something very important, because if you can't trust back really what are the input data, what are the modeling choices we chose, it's really difficult to explain to our stakeholders why the results keep changing from year to year, or if we are doing some benchmarking with other studies, is really to quantify where the changes comes from. So I would say traceability is something very important, and we really take it seriously when we are taking our input data or our assumptions when modeling the MLZ. Before diving into the modeling, I would like just to give you a little bit of glance about the input data set, because I think it's worth mentioning. It's a little bit of a complex process, but I will keep it very simple. As I said earlier, the input data consists of ENSO-E data sets. So for the whole Europe, we take data from ENSO-E. And in ENSO-E, there are different task force. Let's say from the PMDB, we take the available generation capacities, the NTCs, the DSR capacities. From the PECD, we take the hourly profile, for example. From DFT, we take the climate-dependent demand profile, and flow-based market coupling are computed based on synesis collections and power flow specific runs that we do. The Dutch assumptions then are added on top of these input data, because this input data comes in specific format that our model builder needs to take to create the models. So once we get the data, the national trends for other European markets, we add our assumptions for the Dutch study. And this will result in the MLZ input package. So these are the final packages that are fed into our models. I would just like to mention two things here to not confuse you. The maintenance optimization is a layer that is being done outside the process, because we need the generation and the load, because the maintenance is built on the residual load. So this is being done outside. and is something called EVA, it's Economical Viability Assessment. Gabriel will explain that later on at 4. It's an LT run that is done in the ERA process, because resource adequacy do not look only at thermal units if they are available, but we are also looking at them if they are economically viable or not. So that's why in the ERA process, before running the adequacy study, we run a step in LT, and those, it gives us if the capacities that has been used in the national trust, it is economically viable or not. And this is the final results we got as an input data for our model builder. Now we move on how this input data become really adequacy behavior. As I listed, there are many data, but let's check how it's behaving in the stochastic manner. The first thing is the demand. So the demand, it becomes an obligation in the model. You need to meet the demand, otherwise you are having scarcity issues. The weather-driven profile, they become as an hourly availability. So it's either for load or for rest, meaning that scarcity timing will change across climate years. The thermal units and CHP, for example, plant are optimized by their contribution. It's really limited by cost and availability. Battery storages and hydro reservoir, they are not unlimited, but they are limited by their energy capacity, efficiency, and also we have constraints on the hydro storages. The network and market coupling are constrained, so for the Netherlands, imports are not unlimited, but we are heavily dependent on flow-based market coupling. The PTDFs and the round value really directs how the flows and how much of imports we can get. And lastly, we introduce availability and uncertainty through maintenance and forced outages. So every input element becomes a behavior in the optimization, not just a value. Whether it drives the timing, network constraint, they limit the imports, and uncertainty creates this situation where we have scarcity hours. Now let's go to finally to the modeling of in PLEXOS that we use for the MLZ. So we use the typical object mapping like generators, fuel, batteries, storages, emissions, purchasers to the object choice determine whether a unit is consuming, is producing, or it's in the reserve market, for example. Thanks to the time series and time logic and time slices, we are able to make MLZ as an hourly simulation. So all the load, the hydro profiles, and the renewable are becoming as a time series in our models. We also use the time slices to allocate flow-based market coupling to different weather scenarios, because it's a stochastic model, so having different weather scenarios in one model is very important for us. The fuel costs, the variable costs, CO2 emissions are signals, and they set the merit orders and the dispatch in the model. And we also have DSR, and we have it with activation price, or we have also electrolyzers, so we have flexibility activation, which also supports revenues and EVC analysis. Fourth, we have custom constraints and conditional constraints. So the custom constraints help us, for example, to set constraints on the hydro reservoir, on the demand side response. For conditional constraints are very important because in our model there are some constraints like the local matching constraints. I will speak later on because it's in the scarcity analysis part, but it necessitates conditional constraints, which means that you set in your variable a condition, and when this condition is active, then the constraint is either binding or not. Fourth, we have the flow-based market coupling. So we model flow-based market coupling through interfaces. We use the properties flow coefficients to equivalent to the PTDFs, and for the RAM values, we use the max capacity. And last, of course, we have the scenario tagging configuration. So rather than creating multiple XML files, you can have scenarios where you can tag your samples, or you can add all weather scenarios in different scenarios, and then you can enable them within the simulations. I would say that none of these are really exotic PLEXOS features, maybe the conditional constraints a bit, but they are all standards, but the skill is really knowing which mechanism maps to which technology and being disciplined about the mapping. How we run the Monte Carlo simulation. So as I said earlier, in the input package, we have the scenario for all Europe. We have our Dutch assessment. As I said, we have the EVA input data set, and then we set an initial force outage. Then we run an MT and the ST. In our simulations, mostly the MT is related to the hydro storages because they are yearly targets or weekly targets. So the hydro is being optimized within the MT step. And then the yearly and the weekly targets, of course, they are passed into the ST as a daily target. And then we run, depending if it's leap per year or not, we run a full year of 364 days with 1 day, day ahead. Look ahead, sorry. And then we look at, we consolidate all the results, and we look at the conversions of the unserved energy. Because as I said earlier, we are having a combination of weather scenarios and outage samples, and this will give us a final ENS, but the ENS, especially for small countries, cannot really converge. You might have really a big gap between ENS in sample 1 or sample 2, so we try to do different iteration till we have a convergence of the unserved energy. So if we don't achieve convergence, we just increase the number of outage patterns we have in. If we achieve convergence, then we just get the market dispatch outcome. We perform the post-processing for the scarcity analysis, and last we are having our final LOLE and ENS. Now I will speak about this post-processing step. It's called curtailment sharing. It's something that is being performed in the euphemia, in the day-ahead market. It's really complex matter, so I'm really make it very simple here. It's in the model we are having it as a quadratic function, but I'm not going into the details. Just that you understand a little bit about curtailment sharing. So as I said earlier, once we have the outcome of PLEXOS, we feed these results into a post-processing model. We apply two things. The first thing is local matching, which means that net exporter countries cannot have unserved energy. I know that it seems like something very trivial, but when you have flow-based market coupling in your model, as I said earlier, the ENS is allocated randomly in the countries. Even if a country is a net exporter, it might still have ENS. So I avoid that by applying local matching constraint. And later on, I have the sharing rule. So let's say you have different markets. As I said, when you have flow-based market coupling, you see it as a competition between countries. You have different PTDFs, and everyone is competing how much he can get from the RAM, which means that countries with lower PTDF, they might have the maximum of import. You don't want that. What you want that the sharing between the countries of scarcity is proportionally equal to their unserved energy. Just as a simple example, before curtailment sharing, you might have this is as an initial unserved energy in the Netherlands, Belgium, Germany, and France. You see that Belgium, for example, it gets the most of unserved energy simply because it had a bad flow factor competition. But when we apply these market sharing rule, you try to equalize the unserved energy between the countries, and those will be the final results in the model. So without curtailment sharing, domestic supply is matched to domestic demand first, so it's the local matching rule, and remaining scarcity is allocated proportionally, which means LOLE and ENS reflect each country's actual exposures to the limitation of imports. These are the results of the MLZ. Unfortunately, I couldn't show the latest results of this year because they will be published in the 10th of this month. So my colleagues told me that we cannot present them yet. This is from last year. So the result shows that we, as the Netherlands, we don't have any issues in 2030. You can see that our LOLE is lower than 4 hours per year. But in 2033, 2035, our LOLE jumps really high to 12 hours per year and 9.2 hours per year. But because we do the AVC, we look at if let's say the capacity in our models are still viable or not. After performing the AVC, which is based on the revenue-based study, let's say, we found out that 1.7 gigawatts of gas must be in risk, which means it might be not viable. So when we took these 1.7 gigawatts from 2030 target year, we found out that our LOLE might jump to 8.3. So as I said earlier, the MLZ study is really a combination of different processes that can feed in each other. So you cannot trust in only 1 hour. You really need to look at different aspects in your model before make final judgment. And I would like to finish this session by speaking about lesson learned from working with PLEXOS. There are many lessons. I tried just to combine them really shortly in 3 different aspects or 3 different layers. The first layer is the validation. Do not try to build the full model and try to validate either the input or the outcome, because either if you are having a runtime, increase on runtime or infeasibilities, it's difficult really to spot where the error comes from. So our strategy in TenneT is really to build the model progressively and see what is causing runtime issue, what is causing infeasibilities. The second part is feasibility is a deliverable. We mostly tend to really relax the constraint, put in just some price on the constraint and say, if I relax this constraint, the model will be feasible and go on with the simulation. I would say from my perspective, this is wrong. Try really to trace back where the infeasibilities are before thinking or relaxing any constraint, because that's a key. If sometimes you discover it's a bug in PLEXOS, 90% of the time, 10% of the time is your input data problem. Scaling before tuning. At least for our European model, we have, let's say, reservoir ranging from gigawatt hours to PTDFs that are really, really small, like 0.0001. So when you put this in PLEXOS, of course, you need to enable all the time diagnostics, because the normal part, it just gave you the runtime of the model. But you can see that normally PLEXOS tells us that our models are bad scaled, because you are having your matrix at the order of 12 or minus 12, and this is really bad for PLEXOS to solve the solution. But you still have the option to scale down. If, for example, you have an order of gigawatt hours of reservoir, you can scale it down to megawatt hours, and you have PTDFs really small, you can scale them up by multiplying that by 1,000. The scalars is an option in PLEXOS. I would suggest to use it if you have bad scaled model like ours. Solver behavior. Solver settings are assumptions. So, for example, if you increase the numerical focus or you look at the optimality tolerance, this can really affect the results, the quality of the results. So what we do there is in Gorobi, a lot of lists of solvers options. I really suggest that people should really look at the options and see what kind of solvers you can use to make your model more performance. Because sometimes PLEXOS tell you increase the numerical focus to, I think it ranges from 1 to 3, but if you put it at 3, the runtime can be increased by 60% or 70%, then it doesn't worth it. But you also need to look at your optimality tolerance, because if sometimes the optimality tolerance is very tight, the model struggles to find the solution. Of course, it depends on if you are using simplex or another dual simplex or another part, but you need all the time to look at optimality tolerance and try to play around with different values and see what works good for your results. And do not look up at suboptimal parts, especially for the LT plan. Suboptimal can be bad. You also need to look, of course, at the optimality gap. But for our experience, when we are having the empty schedule, we look if the results are optimal or not, because the empty schedule is passing all the information to the ST. You don't want bad information that they are, or not very accurate information that are passed to the ST, because then you end up with infeasibilities in the ST that you cannot really look at. So I would say all the time check if the optimality, if your termination is optimal or suboptimal. From our experience, using flow-based market coupling and conditional constraints really increase the runtime. Till now, we couldn't find yet I would call it a solution for that. We're still checking with the team for Energy Exemplar. Hopefully they can find something for us. And the last part is the engines, and I think this is the most important part. The engines are not plug and play. So for us to move from an engine to an engine, it's a very difficult part. Because when you find an engine, of course you will find a bug with it. Then Energy Exemplar will give you some like workaround on that specific engine, and that you are finding a result. Moving out to another engine, you really need to do benchmarking to understand why the results are changing from part to part. Because sometimes Energy Exemplar are solving some bugs in different engines that you haven't seen in yours, so you cannot really understand why the results are changing. So for us, the engine part is very important. We don't really go quick by going, for example, now the 12 tree, because we already defined our model on specific engine, and we tried to find out all the possible outcomes that are feasible into our modeling. Use a frozen benchmark if you want to move from a model to model, solver settings or features, again, the same input. And that was it from my side.
Do we have any questions?
I think flow-based market coupling, whenever you include that and you also have weather years and you have these complex models, things blow up very quickly. And I'm wondering where you stand in your conversations with Energy Exemplar to simplify flow-based market coupling, just from a... I'm thinking about reducing the number of constraints, maybe putting in more constraints to round up the corners of the domain. But I'm just wondering, what are you thinking? Because I feel like many people say, let's just use NTC, and that's always the simplification people make to simplify. But then we have seen that NTC is actually very different from flow-based market coupling market results. So it feels like it's important to actually do flow-based.
Yeah, definitely. I would say that we don't use NTC anymore. We use flow-based market coupling. We try to implement them through two different methodologies, either through custom constraints or interfaces, but we reach the same problem because we are, as you said, we are having these constraints that are added for every weather scenarios in the model. So it's really difficult that the optimizer find the solution quickly for us. So we are nowhere near to find the solution for that. But what you said about the corner, we do that with our amine subgroup tree in ERA. So we create the flow-based market coupling in there through eBridge. And there we try to take out the corner and assess the results. So we create two sets, either the full sets or reduced sets. And in the reduced sets, we try to take the corners that we think that they are not really affecting the results. And then we can assess which countries are being assessed through the ENS and the LOLE, and the reduced domain can really help in that case. Yeah, they can reduce the runtime rather than the full flow-based market coupling.
Here. Thank you. Interesting presentation. You quickly went over the missing adequacy gap. Have you found a quick and good way to analyze how much capacity is actually needed in several target years for the 4 hours?
It's a very complex run now. It's part of capacity mechanism in ERA. We call it with CM scenarios, but in TenneT we are doing it now simplified. We just do a rerun, multiple rerun with PLEXOS, where we add capacities in all Europe to some extent that we think the convergence, because what you don't want to overestimate the capacity or underestimate the capacity. So we try to do a different rerun, adding a capacity to whole Europe at, let's say, first of all, we draw the unserved energy curve, and from there we can see, for example, how much capacity is needed for the countries to reach, for example, let's say, some targets of the reliability targets, and then we try to add capacity proportional to that gap from unserved energy that they have. For now, we are doing it more simplified, but in the future we are going into more details because of the capacity mechanism part. It's really linked to it. So. But it's really, it's a difficult matter. It also needs another 20 minutes for explanation.
We've probably got time for one more question.
Thank you for the excellent presentation. Dusan Lajsavljević from EKC. I have also one question related to the flow-based. Do you use the 6 regimes, the same ones as in ERA, and map them to weather scenarios, or you do some additional internal calculations, maybe to stress test? I know that TenneT uses the derogation, so do you apply 70% rule, or you play a bit and do sensitivity around the flow-based
We
parameters?
do use in ERA 70% rule to compute flow-based market coupling. We do use that. For now, for the MLZ, it's just because for the NRA and the ERA, if you want, for example, to go to your government for capacity mechanism, you need to be aligned with ERA. So we are using the flow-based market coupling coming from there, which are, even this year, we got 6 domains, let's say, and those 6 domains are allocated to different weather scenarios. We do the same in ERA, but for our IP investments plan model, we create an hourly flow-based market coupling.
Yeah, so for investment, you're doing the full
Indeed,
year?
we do the full year.
And here you comply with ERA? Okay.
Indeed.
Thank you.
For weather scenario, no worries.
Lovely. Thank you for an amazing session.
Thank you.